Okay, so here we'll go and prove the generalized uncertainty principle that we have discussed in class and that I'm writing down right now. So how do we prove this relationship? We actually first need to prove one additional ingredient, and that is the Schwarz inequality for actually any inner product, and that the Schwarz inequality is given by this relationship. And this inequality is true for any two quantum states phi and psi. As a matter of fact, this is true. This is a general property of an inner product. And by that, we should be only using properties of an inner product to actually prove this inequality. Also note that you get the strict equality in this equation only for the case where phi and psi are simply related by a scalar factor. So when they're actually not independent of each other. Okay, so let's first see how we can prove this. So prove Schwarz inequality. That's what we'll do next, and then we'll use it. First observation, or let's make two observations. First one is we call this inequality star. Then we see that star is definitely true if either of the vectors is 0. And then, as we just said, 2 is also true for the case that psi and phi are linearly related. Okay, so we just stated this. And so here, that you can actually verify in a very straightforward way. So if they are actually linearly related, then psi phi, this inner product, is equal to alpha star phi squared, so that is equal to alpha squared and phi squared, and this is equal, observing that psi is actually equal to alpha squared phi. We can rewrite this and indeed get psi phi on the right hand side, and so then we have strictly the equal sign right here. Okay, so then if we want to prove the general Schwarz inequality, we can assume that neither phi nor psi are equal to 0. So psi is not equal to 0, and phi is unequal to 0. And that lets us define then and use quantum state chi, which is equal to phi minus psi phi divided by phi psi. And if you look carefully what chi actually is, it is equal to psi minus the projection of psi onto phi. That would be the geometrical meaning. We are going to use this one and actually manipulate it. If we now form the inner product of phi and chi, what we get is this. And the second term equal to this, and then I get another inner product of psi with itself right here. We observe that these two cancel each other, and what I'm left with is that I have twice this, so in total I actually get 0 here. And this is because, chi was equal to phi, but I had already subtracted, all the parts of phi that were parallel to psi. So then I've created or constructed a vector or a quantum state that is orthogonal to psi. Okay. Why is this helpful? So first of all, this means that psi, psi and chi are orthogonal. At the same time, I can take the definition of chi and rewrite it in terms of phi, or I can express phi in terms of chi and psi by just inverting the definition of chi. So I can write, take this whole part onto the left here, and then I get that phi is equal to chi plus psi phi divided by psi phi. Okay, so that's useful. If I do this, I can now calculate the inner product of phi with itself, which is equal to chi plus this divided by psi plus times the inner product of psi with itself. And note that I omitted any cross terms between chi and psi here because, as we just showed, chi and psi are orthogonal. So all these cross terms that I would generate are actually equal to 0. And so I can further write, that this is equal to, so the inner product of chi with itself, and now I'm just simplifying this term, observing that I have the inner product of psi and psi here, and then I have the inner product of psi with itself squared down in the denominator, so I can simplify this to be equal to psi squared divided by just one term times the inner product of psi with itself, and then the inner product of any quantum state with itself, or any vector with itself, is always going to be larger or equal to 0 and real. So I can, make an inequality here by omitting the inner product of chi with itself and just directly get actually the Schwarz inequality here. So now this is the left side, this is the right side. If I multiply the inner product of psi with itself over, I get what I wanted, the Schwarz inequality. And of course, this should not be an equal sign. Whoops. But what we just proven is that it's larger or equal. Okay. And so now in the next choice piece, we will use the Schwarz inequality to actually prove the generalized uncertainty principle.